Physics Lab 4 Oscillations by Caitlin Schmidt. For the introduction, the mass on a fixed spring is stretched and then released. The position data from release point was recorded using tracker, and the computational model created in GoScript predicted the motion, and the energy changes were plotted using the model. And the assumptions are that the fixed end of the spring is at the origin, the object has a mass of 0.42 kilograms, and the spring's mass is negligible. The system only includes kinetic energy, spring potential energy, and gravitational potential energy. So these are the key principles I used for this lab. I used Newton's second law, which is F net is equal to the change in momentum divided by the change in time, which also includes the velocity update formula and the position update formula. And the energy principle was also used, which is the change in energy is equal to the change in kinetic energy added to the change in spring potential energy, and then also added to the change in gravitational potential energy, and all of those are written down below, and then all of that is equal to 0. So for the tracker analysis, I used this video, and the system is the mass, the spring, and the earth. The surroundings is nothing. The object mass is 0.402 kilograms, and that's the initial position, and then the initial velocity is 0, and I also included a screenshot of the tracker. So these are the computational model initial conditions. I set the mass of the ball. I also put the position vector and the velocity vector, which is the same from the tracker before. And then I set the change in time to 0.095 seconds, and also set gravity, the spring constant, and the relaxed length of the spring. And then also established L, L hat, and S, and then established all of the system energies below. So for the computational model iteration section, which basically just calculates the stuff that we need, we have a while loop, and inside is basically just all of the equations and the key principles. And the next part on the right is another while loop that compares the video analysis measurements to the actual measurements. So these are the graphs that are produced by the code, and we have the change in energy versus time graph, and then the X position versus time graph, and then the Y position versus time graph. So now for the discussion. So for change in energy versus time, the changes in gravitational potential energy and spring potential energy are opposite in sign and oscillate, and the changes in kinetic energy also oscillate, but with a smaller magnitude than the other energies. For position versus time, the Y position versus time graph shows that the model is less accurate at predicting the Y position compared to the X position, and potential errors would be neglecting other forces such as drag, failing to account for additional energies like rotational kinetic energy, and inconsistent marking of the object's center of mass using the tracker. So what does it mean? For the energy principle, yes, the energy principle is satisfied. The sum of the changes in kinetic energy, gravitational potential energy, and spring potential energy equal 0, so the total energy is conserved. And for the oscillation periods from the tracker, the average oscillation period for the X position was 1.706 seconds, and the average oscillation period for the Y position was 1.387 seconds. And the average oscillation period was calculated from the average of 3 cycles. And differences in oscillation periods affect the calculations of the spring constant K, spring force, and the spring potential energy.